This video is on Dalton's law of partial pressures. Dalton's law of partial pressures is relevant because gases often exist in mixtures. And what kinetic molecular theory tells us is that each of the components in a gas mixture exert pressure, and this is because all of the gases are going to be colliding with the container walls, meaning that they're making pressure. And the partial pressure is defined as the pressure exerted by an individual gas in a mixture. There are two equations that we use. The first one is that the P total equals the sum of each individual pressure, so P1, P2, P3, all the way up to Pn, where Pn is a partial pressure. And the second one is that the partial pressure can also be defined as the total pressure multiplied by the fraction of gas 1, and the fraction of gas 1 is represented by x1. The first question is that the atmospheric pressure of air is 1 atm, and to calculate the partial pressure of each gas in the air. And so if we use the equation P1 equals P total times the fraction of 1, we can plug this in for each component. So you'll see we have the total pressure multiplied by the fraction, which we were given in this table, and then we can solve for the partial pressure of nitrogen. The same can be done for all the other gases. Question 2, what is the partial pressure of O2 in air that is 783 torr? In this case, 783 torr is P total, and then we can do the same thing as we did before, getting an answer of 155 torr. Pause and try question number 3. An application of Dalton's law of partial pressures is collected over water experiments. When the product of a reaction you are trying to collect is a gas, it must be collected somehow. The best method they've found is to collect a gas over water to ensure that your sample is only mixed with water vapor and not also nitrogen, oxygen, argon, etc. that are found in the air. Consider the reaction of zinc plus HCl. We get hydrogen gas plus ZnCl. Typically, we would drop in solid zinc into an aqueous solution of HCl. However, when it reacts, we end up bubbling H2 out of solution, and then we're not able to collect it if we wanted to sell it or use it in a different reaction. This is what the setup initially looks like. We have a stoppered flask. We can drop in our zinc metal, and it goes into a basin of water with a beaker up at the top in order to collect the gas. So that when our gas is produced and starts to go into the water, it'll end up displacing. And up in this space, we have the area of collected gas, which has H2 and H2O. You may wonder why we do an experiment where we still mix our gas with water vapor. And that's because the partial pressure of water vapor is distinct at every single temperature. And so this information has been well researched and can be found in tables such as the one below. So you'll see that at each temperature, the pressure of water vapor is fixed. So you're able to actually determine the pressure of just your gas through the summative equation above. In question 4, we collected hydrogen to a total pressure of 758 mmHg at 25 degrees C. What is the partial pressure of H2? You'll see that the partial pressure of water is given, and it's known information that has to be given to you in order to solve a problem. Now try number 5 on your own. Next, check out this video about collected over water. I want you to think about these 3 questions and then come back. I hope that you found that the reason why it's important to have test tubes is to capture gas. We need the test tubes to be filled with water to avoid mixing with air. And that is beneficial to collect gas in a graduated cylinder because you could measure volume. There are a couple of steps or tips to help you do problems. 1, always correct for pressure if you have a collected over water experiment, which means that you subtract the pH2O. 2, label everything, units and compounds. Number 3, only use gases in gas law equations. 4, when you're using the ideal gas law, you must use liters, ATMs, and Kelvin. And number 5, round for sig figs at the end of your total calculation. So question number 5 is a stoichiometry problem that includes a collected over water portion. The problem gave us the following information: the total pressure, the volume, don't know moles, we know temperature, and we're solving for the grams of aluminum, which means that we must end with our stoichiometry. So the first step is to adjust for the collected over pressure. Step 2, we're going to use the ideal gas law to solve for moles of H2. Now that we solved for moles of H2, we can now use the molar ratio to convert to moles of aluminum and then grams of aluminum using molar mass. Our final answer is 0.139 grams of aluminum. Question 6 is interesting because we're actually comparing two different scenarios. We have the first condition, and then the second condition is SDP. That means instead of using ideal gas law, we're actually going to use some sort of comparative relationship such as Charles, Boyle's, combined, Avogadro's. So let's find out what information this problem gave us in order to determine which law we're going to use. Now that we know that we're changing pressure, volume, and temperature, and we're keeping our amount constant, which means our moles are constant, we're going to be using the combined gas law. Using the combined gas law means that we can keep our units of pressure and volume in whatever we want. So let's just keep it consistent. We'll use torr and milliliters. First step is going to be adjusting the partial pressure. Next, we're going to use the combined gas law to solve for V2. Final answer of V2 equals 28.7 milliliters. We were given the following information. Now I'm going to write down the 3 steps you need to do, and then I want you to try to solve it on your own. Go ahead and try the problem.